Okay, hello everybody. We're going to be working on homework number 5 today. And there's 12 problems in this. And here is the first problem. 5 forces act on an object. 60 newtons at 90 degrees, 40 newtons at 0 degrees, 80 newtons at 270 degrees, 40 newtons at 180 degrees, and 50 newtons at 60 degrees. What is the magnitude and direction of a sixth force that puts the object in equilibrium? Okay, the first thing we need to do is to draw a diagram and have a general understanding of what's going on. Okay, so here's the object. It's the square object right here I'm pointing to. And this is 40 degrees at 0 degree, 40 newtons at 0 degrees, which is just moving it to the right. There is 40 newtons at 180 degrees, which is moving it to the left. There's 80 newtons, which is essentially just pushing it down. And there's 60 newtons, which is pushing it up. And there's 50 newtons, which is pushing it at a 60-degree angle respective to the horizontal. Now, to make this our life a little bit easier, we can make out some pretty obvious first observations. It's very clear that 40 newtons, they both cancel out. But this one, the y direction is 20 newtons down. And if we split the force here, we calculate our x direction to be 25 newtons, and our y direction to be 25 squared to 3 newtons up. And in order to find that, we need to do 60 newtons up plus 25 squared to 3 newtons up minus 80 newtons, which is down. And we find that our y direction is 23.3013 newtons. This is our net y. And from this, we can, and from earlier, since we know that the x direction is 25 newtons and the y direction is 23.3013 newtons, we can draw a diagram of what our sixth force should look like. So to cancel out the forces, we moved 25 newtons to the left and 23.3013 newtons to the downwards. And all we need to do right now is to take the inverse of that. As you can see, it's clearly shown here. And in some cases, you might get lucky, but and just get the answer directly. But in some cases, you might have to add 180. How you make sure you add 180 or not, make sure that it makes common sense, okay? Make sure that it goes in the general direction. Because for me, in this case, I actually had to add 180 degrees to get my direction at 222.9858 degrees. And to find the amount of force we need, all we need to do is use our Pythagorean theorem. A squared plus b squared equals c squared, pretty standard. And we find out that our force, our magnitude, is 34.1752 newtons. And this makes our final answer 34.1752 newtons at 222.9858 degrees. Okay, on to number 2. We see that the problem says a 0.4 kilogram ball is dropped from a tall building. The acceleration of the ball is negative 9.8 meters per second squared. What is the acceleration of the Earth if it has a mass of 5.98 times 10 to the 24th kilograms? This is really easy to solve if you know Newton's third law. Remember that Newton's third law states that every force has an equal and opposite reaction. And thus, the force is equal because Newton's third law says so. And we get our first force, force 1 if you want to call it, which is the force of the ball that is falling onto the earth. And we also have the force of the earth, which is our mass times our acceleration, which we don't know at the moment. And once we solve for A, we get A to be about 6.555 times 10 to the negative 25th meters per second squared. Or you can write out a bunch of zeros like me. I'm not sure why I did it, but I did it. But please just write in scientific notation. It's much easier to understand. But this is our answer for number 2. Okay. All right. Let's move on to number 3. And the problem says, the maximum force a grocery bag can withstand and not rip is 250 newtons. If 20 kilograms of groceries are lifted from the floor to the table with an acceleration of 5 meters per second squared, will the bag hold or rip? Okay. First off, we need to calculate our force weight. Pretty standard. It's just m times our g, which is 20 kilograms times 9.8 meters per second squared to get 196 newtons. Force weight plus the force up equals our net force. And our force up is 20 kilograms times 5 meters per second, which is our acceleration here, to get 100 newtons. We add the two forces together to get our net force, and we find out to be 296 newtons, which is greater than our 250 newtons limit that it set in the problem, and thus the bag will rip. Okay, moving on to number 4. The problem says, the force required to move an 8.24 kilogram metal cube across an oak floor is measured. The force needed to start the cube moving is found to be 42.8 newtons, aka our static friction, while the force required to keep it in uniform motion, which is our kinetic friction, is 32.5 newtons. Calculate the coefficients of static and sliding friction for the two materials. Okay, we have our picture here, like for every problem, well, almost every problem, and we have our object of 8.24 kilograms. We draw a force applied to the right, and we draw our force friction to the left. Force normal, again, is always perpendicular to the surface of contact, and force weight is just mg, so it's obviously coming down. And static friction is just enough friction to get the object moving. And if you remember from the last video, we can set force applied equal to force friction. And we already know that force normal equals force weight. In essence, and we know that force friction divided by force normal equals mu. In essence, we can just substitute these variables into our mu equation. And we first calculate our net force with the 9.8 meters per second squared, which is our g, and the mass of our object, 8.24 kilos, and we get 80.752 newtons. And because our force friction is 42.8 newtons, again, they equal each other, and we plug this into our calculator, and we find that our mu variable for static friction is 0.53. And for part 2, because we already knew our force normal, the force friction just enough to keep it in motion again. This is force applied equals our force friction, just enough force to keep it in motion again, is 32.5 newtons divided by 80.752 newtons, which we already solved, and thus we get our kinetic friction to be 0.4025. Okay, number 5. A street lamp weighs 150 newtons. It is supported equally by two wires that form an angle of 150 degrees with each other. What is the tension of each of these wires? Okay, first off, we're going to split the force. So this is 150 newtons, okay? And we have force Y, force X, and force X. We split the force. Now, if you remember from our first unit, the X and Y directions do not affect each other. So just ignore the X direction at first and just focus on the Y direction. Again, the problem states that this is supported equally by these two wires. So the force has to be split evenly between these two force Y's. And that means that it has to be 150 divided by 2, which is 75 newtons. And 75 newtons, we can just take tangent 15 degrees equals 75 over X, force X, and we eventually find out to be about 279.9038 newtons. And that's our force for X, and we know our force for Y, and all we need to do, oops, I forgot to square there. All we need to do is plug in the Pythagorean theorem to get our answer of 289.7777 newtons. And the answer key, if you look up the answer key and scan the QR code, it says 298, but the teacher made a typo and switched the numbers, so it's 289.7777. So don't be confused or anything from this. Okay, we are moving on to number 6. The problem states, a daredevil circus elephant is falling towards a small pool of water. If the elephant falls 55 meters, determine the drag force acting on the 5,000 kilogram elephant after 4 seconds of falling. Okay, first off, we're going to assume there's no air resistance. If there's no air resistance, how much force is there going to be? Again, force weight equals mg, pretty straightforward. That's 49,000 newtons. And to find out acceleration with a resistance, we have 1/2 at squared. Remember, we don't need the v0t part because our starting velocity is 0 because it's falling. And that means that it's just 1/2 at squared. And we know our x to be 55 meters. We know it took 4 seconds. So that means that once we plug it in, we find that a equals 55/8 meters per second squared. And we plug that in to get 34,375 newtons. And here's our equation, our total net force plus our F net plus F drag equals FA. So our total net force exerted is 34,375 newtons plus our F drag, which is essentially, I guess you could call speed that we lost, equals the force applied, which it would be the speed if there was no air resistance. But because this air resistance, which is just another word for F drag, we solve that, we subtract, and we find our F drag to be 14,625 newtons. Okay, got it? Good. All right, number 7. You are driving a 2,500 kilogram car at a constant speed of 14 meters per second along an icy but straight and level road. While approaching a traffic light, it turns red. You slam on the brakes. Your wheels lock and the tires begin skidding, and the car slides to a halt in a distance of 25 meters. What is the coefficient of sliding friction between your tires and the icy road? Okay, we're going to have to go back to Unit 1 for this. If you remember, we get our givens. We have our object of 2,500 kilograms. We have our x, our displacement, which is 25 meters. Our initial velocity is 14 meters per second. And our final velocity is 0 meters per second because, again, you came to a stop. And we arranged the equation that we got because, again, we want to solve for acceleration. And you'll see why later. And so all you need to do, punch those numbers into your calculator, and our acceleration is 3.92 meters per second squared. And I don't know why it's negative there, but 2,500 kilograms times 3.92 meters per second squared equals 9,800 newtons. So that's the amount of force. And our force weight, which, sorry, I forgot to label all of it, but force weight is, again, just mg, which is 2,500 kilograms times the acceleration of gravity, which is 24,500 newtons, which is our force normal. And given that we already know that mu is force friction divided by force normal, we get 24,500 newtons, which is force normal, and our force friction is 9,800 newtons to get 0.4. And you may say, why is force friction 9,800 newtons? Because that's the amount of force you need to get it stop moving. And I have an idea of it, and I have like a good idea you can think of if you're confused with it. Imagine if you're on a frictionless surface and the car is coming to you at 14 meters per second. You were just still there. The car hits you at 14 meters per second, and assuming you're strong and you don't fall and all of that stuff, the amount of force you put on is 9,800 newtons to get the car to finally stop. Essentially, your friction. I don't know if that helps. Hopefully it does help, but sometimes that's how I like to perceive it. And anyways, our answer is 0.4. Okay. Number 8. Unusually familiar problem, because this was actually quite familiar to our previous homework. And it says that a 9.05 kilogram picture is held against the wall with a force that is 40 degrees from the vertical. The picture is not held with enough force, so it is sliding down the wall at 1.45 meters per second squared. Determine the magnitude of the force applied to the picture if the coefficient of static friction between the wall and the picture is 0.560. Okay. It's pretty similar to the other problem we had in the last video, but we have to calculate the newtons of force that's coming down, the total net force. That's 1.45 meters per second squared times 9.05 kilograms equals 13.1225 newtons. Net force, force sine 50 plus force friction equals force weight minus our force net, which is net force, which is 13.1225 newtons. And we get F sine 50 plus F plus 0.56 F cosine 50 degrees. Again, because it's similar to the previous problem, we just substitute in, and that's what we get. And we get that to be 75.5675 newtons. Factor the F out and divide by this huge chunk. And we get F to be about 67.1111 newtons. And the reason why it's minus is because essentially it's helping it. So that's why it's minus. I know it doesn't sound that clear, but once you get used to it, it'll start clicking to you. So that is our answer, and on to the next problem. And number 9 says, a fisherman is fishing from a bridge and is using 45 newtons of test line. In other words, the line will sustain a maximum force of 45 newtons without breaking. What is the rate of the heaviest fish that can be put up vertically when the line is reeled in, A, at a constant speed, and B, with an acceleration whose magnitude is 2.0 meters per second squared? Okay, first one, part A is really easy. Force weight equals the force up, pretty easy, 45 newtons. It says at a constant speed. So it's kind of like the static friction problems on a flat surface, if you want to think about it that way. Part A, 45 newtons, pretty straightforward. Part B, though, is a little bit more complicated, but not too much more complicated. 45 newtons equals 2 meters per second squared times our mass plus 9.8 meters per second squared times our mass. Solve that in for our mass, multiply that by 9.8 to get an answer of negative 37.3729 newtons. And as expected, it should carry less weight because obviously it's accelerating, so there's more force applied because of mg of force weight. Because of the acceleration of the object. So yeah, that's pretty much it. That's it for number 9. Alright, number 10. The problem says a 205 kilogram log is pulled up by a ramp by means of a rope that is parallel to the surface of the ramp. The ramp is inclined at 30 degrees with respect to the horizontal. The coefficient of kinetic friction between the log and the ramp is 0.900, and the log has an acceleration of 0.8 meters per second squared. Find force tension in the rope. Okay, number 10. Lots of forces into account. We got force parallel drag trying to drag us down, force friction trying to drag us down, and we have force perpendicular, force normal, and obviously our acceleration of 0.8 meters per second, which is going up. And we also know that our mu is 0.9. And let's calculate our force normal, which is just force perpendicular. And we're lucky this time because if you remember your 30, 60, 90 triangles and the tangent, cosine, and sine of them, we are in luck. So force normal, punch them in when we approximate them to being 1,739.845 newtons. And our force friction, because we get from our equation of mu, is 0.9 times force normal, which we just solved for. So we get our force friction to be 1,565.8605 newtons. And because force friction is equal to force parallel, but you got to add that too, because you also got to calculate the acceleration of the object itself. 0.8 times 205 kilograms, which is the object acceleration of moving up. Then we get that answer, but you also have to add force parallel too, which is again also dragging us down, which is our gravity. And again, force parallel is mg sine theta, plug all those numbers in, and we get our final answer to be 2,734.3605 newtons. And I cannot be more clear about this. Every picture, every problem, unless it's a really, really easy one, you gotta draw a picture. You gotta draw a picture to make sure everything's organized and make sure you don't miss a force or add or subtract things wrong. I cannot stress how important this is. I know it may be a pain in the butt, but you gotta do it. And this is our number 11. Again, this is number 11, the pulley problem. And it says the weight of the block on the table is 422 newtons, and that of the hanging block is 185 newtons. Ignoring all friction and assuming the pulley to be massless, find the acceleration of the two blocks and the tension in the cord. Okay, let's just call 422 newtons force weight 1. And 185 newtons force weight 2. Just to make our lives a little bit easier, not have all this jumbleness. And force weight 1 equals mg. Plug all of those numbers and we find our mass to be about 43.0612 kilograms. And we find our force weight 2 of 185 newtons. Again, you plug it in to get 18.8776 kilograms. Remember, from our first unit, we learned that the x and y do not affect each other. Remember, it doesn't seem like it's moving in the y direction, but that's because we have support from here for force normal. but force weight is still there pulling on it. So just to relieve some confusion, again, ignore the x direction because, again, the x and the y aren't affected. So that's why we add the two masses together to get our mass to be 61.9388 kilograms. And then we get our force of 185 newtons because that's the one being directly pulled by gravity. We do 185 newtons divided by the answer we just got to get our acceleration of about 2.9868 meters per second squared. Now we need to find our force tension. And how we calculate that is 185 minus the force acceleration of our object, which we just found earlier. And we take this number and we take this number and multiply it by, let me say this again. Force tension equals force weight minus force acceleration of the object. And so, in essence, we take the acceleration of this object times the mass we just got for the 185 newtons. Okay, hopefully that makes a little bit more sense. I got myself a little bit jumbled up there for a moment. But anyways, you multiply these two numbers together because essentially this is kind of like, if you want to think about it, like your air resistance, sort of, like if you want to think about it that way, like, if you're thinking back to number 7 of the skydiver problem, if you want to think about it that way, that personally helps me, but do whatever makes you feel the best. So again, we multiply these two numbers together, 185 newtons minus those two numbers we just multiplied to get our final answer of 128.6161 newtons. And on to our very last problem, number 12. Two forces, F1 and F2, act on the 70 kilogram block shown in the drawing. The magnitudes of forces of force 1 equals 59 newtons and force 2 equals 33 newtons. What is the horizontal acceleration of the block? Actually, I find this problem to be pretty easy, even though it says it's an honors problem. So usually it's supposed to be harder, but it's pretty straightforward. All we need to do is split the force. So 59 newtons, Fy equals F sine theta, and Fx equals F cosine theta, and obviously our F is 59 newtons. And depending on your reference points, you can either set this to be positive or negative. Personally, I think it should be better to set this to positive and negative, but I made this positive. So we find F cosine theta, 59 cosine 70 degrees. Subtract the forces to get our net force of 12.8208 newtons. And since it's asking for the acceleration, we divide up by a mass of an object of 70 kilograms, and we get 1.8315 meters per second squared, or negative, depending on your point of view. It's better to be negative, but I did it this way because I felt like it. And that is it for homework number 5. Hopefully this video helped you, and hopefully you get a better grasp of physics. Alright, see ya.